Hey folks, welcome back. So in this third and last video for Lab 3, I'm going to tackle example 2 here in the lab handout. And this is a one-way ANOVA, so we're still dealing with a single factor CRD, but now it's a nested design. And what that means is that we have subsamples. We are subsampling within experimental units. And the layout of the experiment is this. We have a bunch of mint plants that we're growing, and we're applying different growth treatments to them. And those different treatments are being applied at the pot level. In other words, we have plants growing in pots, and it's the pots to which we are randomly allocating treatment levels. So we have 3 replications, true replications, or 3 pots per treatment. But now we have things within the experimental units that we're measuring, and those things are the plants themselves. We have 4 plants within each pot, and here's where we get the terminology of 4 subsamples within each replication. And let's go ahead and start. So this is the workspace where I was, and I just learned a cool trick, so I'll tell you. I have a messy console. I can clear the console really easily using Control L. Oh, I think. Let me get back here. Control L. Boom. Goes away. That's really nice. I can use the little broom over here to sweep up everything I was doing before. And now I have a blank slate. So let's go ahead and open up example 2 so we can talk about it. Here it is. And this is a script that performs a one-way ANOVA for a perfectly nested CRD and finds the variance components. And I stress that again as I did in lecture. The only reason you should maintain subsampling structure in your data set when you run an analysis of variance is because you are interested in the components of variance. If you are not interested in the components of variance, you should simply average over all the subsamples and use a single value for each experimental unit, and that puts us back into the simple CRD case like we saw with example 1 in this lab. Let's pull in the data set and see what we're dealing with here. Example 2 CSV. Here it is. There are headers. I'm referring to this as mint.dat in the script. So let's bring it in like that. And let's take a look at the data set. So structure of mint.dat. And what you can see is that this particular data frame has 4 columns to it. The first column is treatment. This is our true classification variable in our CRD. And it has 6 levels. And R thinks it is really a factor because these are text strings and not numbers, so we don't have to assign it as a factor. R already picks up on that. Now in example 1, we had simply treatment and the response. But here we have 2 additional columns. This column, pot, is the column for the experimental units. This is the replication column. And we've never had to specify the replication column before because replication did not appear in the general linear model in the sense that any variation you had among experimental units within a treatment was error. So that was part of the error term, really. But now we have a different error term. We have a finer scale error term, a subsampling error, in which we have variation among plants within a pot. And this variation among subsampling error is our truly residual error in our model. This is what the epsilon term is going to refer to. And what that means is that the variation among experimental units has been pushed out of that residual error and now must appear explicitly in our model. And because of that, we actually need a column that is dedicated to that ID, and this is why we have pot 1, pot 2, and pot 3 per treatment condition. Now the big difference between pot 1 and condition 1 has a coherent meaning across the entire experiment. Condition 1 is a set of growth conditions that always means the same thing across the whole data set. Whereas pot 1 is just a placeholder in the sense that pot 1 within condition 1 has nothing at all to do with pot 1 within condition 2. Pot 1 has a different meaning within each of these, and for that reason it is simply a placeholder. This is one indication to you that this is not a true classification variable, but that is an indication of your experimental unit. Okay, so let's go back to our script. And what we're going to do is we're going to calculate the components of variance for this particular study. Again, because we may have a study in the future in which we would like to address this question of optimal resource allocation. How many subsamples should we have? How many experimental units or how many replications should we have based on their differential costs and how much information each provides us. To get to these components of variance, we are going to have to bring in a package that is not part of the base installation of R. And that package is the LME4 package. It is a linear mixed effects model package. And for you to get that on your computer, you're going to go to Install Packages and type in LME4. It'll pop up. Click it, hit Install, make sure it's going to install all the dependencies for it, and you'll be good. It'll show up then, after that installation, it will show up within your list of installed packages on your machine. Even though it's installed, however, it is not available to you in any given work session unless you activate it, and that's what clicking the box here is going to do. So I'm going to activate my LME4 package, and generally it takes a few seconds for it to activate because it does have various dependencies that it has to activate as well. But it'll eventually activate, and then once it does, you'll have access to the functions within that package. And the function we're going to use is this LMER function, this linear mixed effects model function. Like the LM function, so this is kind of a variation on a theme, we're going to use LMER, and then what it acts upon is a general linear model. And this is going to be the general linear model that we feed to the LMER function. It looks a little bit funny, and that's because LMER has some strange syntax to it. It starts off with our response variable followed by the tilde. So like LM, our response is explained by the stuff on the right. It's certainly explained by treatment, by the treatment group that it's in, so that doesn't look weird. What does look weird is this statement right here. This statement is building the experimental unit itself into the general linear model. But it looks different from treatment, because whereas treatment is a fixed effect, if we were to repeat this experiment again, whatever growth condition 1 is, we would apply that same growth condition 1 in a future experiment. It's a fixed effect in the sense that our levels of treatment are not being randomly chosen from some population of treatment effects. Pot, however, is not a fixed effect. Pot is a random effect in the sense that if you were to run this experiment again in the future, you most likely would not use the same however many pots you used this time around. These pots come from some universe of pots that you've randomly chosen, the 30 or 40 or however many you need for a given experiment. And because pot is a random effect, and every time you have a replication is a random effect. LMER uses the syntax of parentheses, and inside the parentheses is a 1 followed by a pipe. That is the syntax for declaring a random effect within the LMER model. And this random effect pot is nested within treatment. In other words, if you were to look at pot 1 as a label all by itself, pot 1 is not very informative because pot 1 appears at multiple places within the data set. You have to tell me not only pot 1, but you have to tell me the treatment you're talking about as well for me to uniquely identify what you're talking about. And that's why the random effect is not just pot all by itself, but it's this interaction of pot with treatment, or it's pot nested within a treatment. Pot only has meaning once the treatment level has been specified. And this is how you would accurately declare the pot random variable within the linear model. So what we see here is that growth is explained by some fixed effect and also some random effect. And as before, we don't have the grand mean in the model, and we also don't have epsilon in the model. Epsilon in this particular model no longer refers to variation among experimental units. It's no longer an estimate of the true experimental error. It is now the variation among subsamples within an experimental unit. And so therefore, it is an estimate of the subsampling error, not the experimental error. Anyway, that's our model. We have to specify the data set, and when we run it, I'm going to assign it to a model object that I'm calling ment cv.mod, so that's ment components of variance.mod, And there we go. And I can look at the summary of that. And go up here, and what you will see is that we have random effects in the model. And this is the table you want to look at. We have random effects in the model. And the two random effects we have in the model are the replication, the experimental unit. So this is the pot. This variance is the variance component attributable to differences among experimental units within a treatment. Residual, on the other hand, this is the variance attributable to plants within pots. In other words, this is the variance component associated with your experimental units or your replications. This is the variance component attributable to your subsamples. And these are the exact two variance components that we found in class manually using our expected mean squares, and these are the exact values that you would plug into your resource optimization formula. Again, the only reason you would keep subsampling in the model is in order to find these components of variance. And the reason for that is if you were to actually perform an ANOVA with this particular data set the way it's formatted, in other words, if you wanted to ask, are there actual differences among treatment levels, you would have to run a rather complicated ANOVA. And I would bring your attention to line 22 here. I would have to run an LM model where growth is a function both of treatment and of pot within treatment. Now you notice with an LM model, I'm not making any differentiation between fixed or random effects like we did in LMER. Where that's going to come into play is how we deal with our F-test later on. So this pot within treatment is very similar to what I was describing up here. Pot only makes sense if you specify the treatment level, and treatment, of course, stands alone. We can run that model. What I have above here in line 19 is a shorthand for this. If you just do treatment / pot, that is shorthand in R for treatment by itself plus this interaction of treatment and pot. So if you run either one of these models, you end up getting the exact same result. But I'll run this bottom one to be more explicit about things and get the ANOVA table. And what you see is indeed you have a row in the ANOVA table attributable to treatment effects. You have a row attributable to variation among experimental units. And you have a row attributable to true error or variation among subsampling units. If you were to look at this, you would conclude, based on this p-value, which is very, very tiny, much lower than 0.05, that there must be significant differences among treatments. And if you were to do so, you would be wrong, because of that particular p-value is based on this particular f-value, which itself is based on a ratio of the mean square treatment to the mean square subsampling error, which is the incorrect error term to use in a nested design like this. The correct error term to use is the true experimental error, which is this mean square, this 2.153. And R is not going to give you this in this ANOVA table. You need to know what's going on. And so if you want the right F-test for treatment, you have to do it yourself. And that's what I have up here in the script. I'm going to create a new F value where I have the right thing in the numerator, 35.928, and the right thing in the denominator, the 2.153. I'm going to calculate that F, and you see that I get a value of 16.7, which was much lower than this 38.5. It's a very different F value. And now if I want the probability associated with that F, I can use the PF function in order to extract that probability. And I feed that PF function the F value I just calculated, the degrees of freedom for treatment, which is 5, I get that from the ANOVA table, and the degree of freedom for the experimental error, which is 12. I get that from the table as well. I turn off the lower tail because I want to know what the probability is of getting an F of at least an F that's at least that big under the condition of a true null hypothesis. So I can throw that to R, and what I get is a p-value, which again is quite small, much lower than 0.05, so we would reject the null hypothesis, but it's 11 orders of magnitude bigger than what we saw before. But this would be the correct p-value to use. In example 3, I've done this exact same analysis, having just averaged the subsamples, and you will see that you get to the very same result in a much, much easier way. So again, you would only do this nested design if you were interested in the components of variance. Okay, that's it. Take a look at the lab and get familiar with it all. Thanks.